So in the reading, what we covered was dependency parsing and transition-based methods to dependency parsing. This time I'm going to be talking about transition-based parsing with neural nets. So this is plus neural nets, and this is also plus the fact that you can use transition-based parsing for other things as well, not just dependency parsing. So I'll try to talk about both of those. So up until now, we didn't talk a huge amount about like linguistic structure, like tree structure, that much. And there are multiple types of linguistic structure that we might want to model for various reasons. Dependency structures focus on the relations between the words, like this, whereas phrase structures focus on the structure of the sentence like this. So we kind of skipped over the phrase structure part because kind of dependencies are the main thing that people are doing nowadays, but phrase structure is also another type. So parsing is predicting the linguistic structure from the input sentence, and we have transition-based models that basically step through actions one by one until we have an output. These are like the history-based models that I talked about for part of speech tagging. So we talked about, something like an encoder-decoder model for part of speech tagging, for example. And we also have graph-based models, which we'll talk about next time. These calculate the probability of each edge or constituent and perform some sort of dynamic programming. And this is like the CRF model for the part of speech tagging, where you had a dynamic program that was included therein. So for shift-reduced dependency parsing, this was covered in the reading a little bit. First, why dependencies? So dependencies are often good for semantic tasks, as related words are close in the tree. And it's also possible to create labeled dependencies that explicitly show the relationships between words. Another reason why people use dependencies is they found it a lot easier to annotate dependencies for languages other than like English that have more complicated word order or structure. So one of the reasons why people used kind of phrase structure parsers was because, a lot of kind of the work in linguistics started out on English or other European languages, especially Romance languages. And it started out there, but recently, one of the reasons why we've seen a huge shift to things like dependencies is because these are easier to define for other more different languages. So some examples of tasks where dependencies can be useful. Has anyone like used dependencies in any of the work that you've done? What kind of things have you used it for?
I tried it for some
question answering. Okay. Question answering. Okay. Any other examples? Another task where people have used dependencies or other syntax very widely is semantic role labeling. So question answering, you basically want to take a question and answer, and give the answer to the question. Semantic role labeling is basically finding out who did what to whom in what way, etc. So like if you had here, the semantic role would be C, like to see. The subject of that would be I, and the object of that would be telescope. So you can see that oh, sorry, no. I failed my own parse. The object of that would be girl, and then the instrument that you use to do the seeing would be telescope. So there are these things called semantic frames that are basically like, if you are seeing something, who did the seeing, what did they see, what did they use to do the seeing, at what time did they do the seeing, etc. And there's also lots of use for syntax in that. Because once you have the dependency syntax, you're most of the way there to getting that kind of thing. So in ARC standard shift-reduce parsing, like was in the reading, basically we process the words one by one from left to right. We have two data structures. One important thing when we talk about neural algorithms for dependency parsing is to understand these data structures well, because the neural models are essentially used to model these data structures. So the first one is the queue of unprocessed words that we haven't processed yet. The second one is a stack of partially processed words or subtrees. And at each point, we choose to shift, reduce left, or reduce right. So this was called arc left or arc right in the reading, but it's also often called reduce left or reduce right. And then we learn how to choose each action with a classifier. So an example, we have the root on the stack in the buffer. The queue is also called a buffer. I'm not being very consistent in my explanation here, but the buffer is I saw a girl. We do a shift to get I, a shift to get saw. Oh, sorry. That should be reduce left. So reduce left to get I saw with a line between them. Sorry, I have an off by one error in my slide, I guess. I don't know how that happened. But this is reduce left and then shift. And then we shift again. We reduce left to get a girl as a single subtree. We reduce right to get girl as saw. And then we reduce right to get saw to be a child of the root. And then we're done because we have no more, we only have one thing on the stack and we've cleared out everything in our buffer. So this is the example of arc standard dependency parsing. But the whole idea of like shift and reduce actions is a way to generate trees, can be applied to a whole bunch of other things. It can be applied to phrase structure parsing. It can be applied to semantic parsing, where we want to get a semantic, some sort of semantic structure out of the input as well, which we'll talk about next time. The time after next. So the classification for shift reduce, given a configuration, which is the stack in the queue or the stack in the buffer, which action do we choose? So we might want to choose shift, in which case we'll get the next configuration, left, in which case we'll get this configuration, and right, in which case we'll get this configuration. So making classification decisions, as was noted, we can extract features from the configuration, what words are on the stack or buffer. For example, what are their part of speech tags? What are their children? And feature combinations are really important. So for example, the second word on the stack is a verb, and the first one is a noun. So what this is saying is basically we have a verb and we have a noun. So nouns are very often children of verbs. So if we have this particular configuration, then the right action will be very likely. So up until neural networks came around, like a lot of other tasks, we would create the combination features by hand. And there's a whole paper by Zhang and Nivre, which basically is like, oh, we created a ton of features for this, and now this was state-of-the-art really fast parser for a long time. But luckily now we can use neural nets, which means we don't have to design as many features by hand, and it allows us to take into account more interesting things. So one example of a more interesting thing that neural networks can take into account that wasn't easy to take into account before is a telescope is something that tends to be used as an instrument for seeing, for example. It's not as common to see a telescope as it is to use a telescope as an instrument. So that's something that would be really hard to create with manually created features, and it's a lot easier now that we have word embeddings, for example. Okay, so this was just overview of the reading mostly, and then I'm going to go through a bunch of models and methods that we use for parsing with neural networks. The first example is a feed-forward neural model for shift-reduce parsing. So basically the idea here is what we want to do is not have to design all the feature combinations ourselves, but rather offload the learning of the feature combinations into a neural network. So basically, the idea here is normally what we would do is if we had a whole bunch of words on our stack, we had a whole bunch of part of speech tags for the words on our stack, or buffer. We had arc labels of the previous arcs that we generated, etc. So like we had the n subj arc that we've just generated. We essentially concatenate all of these into one big feature vector. These are all embeddings. So we have word embeddings, part of speech embeddings, and arc label embeddings. And we run them through a hidden layer. Then the question becomes, what features do we want to extract? The way they did this was by taking the top 3 words on the stack in the buffer, which is 6 features, or 6 essentially embeddings. Also, the 2 leftmost and rightmost children of the top 2 words on the stack, 8 features total. The leftmost and rightmost grandchildren, so this is basically, you take the left child and left child of the word on the stack, the right child and the right child of the word on the stack. So this gives you 4 features because you do these for these 2. And part of the speech tags of all of the above, which gives you 18 features, and arc labels of all of the children and the grandchildren. So you take all of these, you take embeddings from them, and you run them through a nonlinear function. In this case, they used a kind of unusual nonlinear function, the cube function, which basically takes the cube of the input value vector, like this. The reason why we do this, it takes a linear transform of all of the inputs and then takes the cube of this. The reason why this does this is it gives you the ability to directly extract feature combinations of up to 3, essentially up to 3 different levels. And before neural nets, the methods that we used for performing this feature combination were support vector machines. And support vector machines with polynomial kernels of a certain order can also extract feature combinations. And if you set your polynomial kernel to 3, you could essentially do the same thing that they're doing here. So they were motivated by the previous methods in order to do this. You can see this because basically, if you look at the scores of each of these, you have weight I, weight J, weight K, multiplied by these 3 values. And you can see you can kind of extract like all 3 features together like this. The result of doing this was much faster than most standard dependency parsers. The reason why was because it's very quick to look up these features and do a matrix multiply over them and then take the cube, as opposed to like manually created feature templates where you have to like explicitly concatenate things together, and etc. So this is able to parse about 1,000 words per second. They also used a pre-computation trick to cache the matrix multiplies of common words. So this is a very nice trick if you want to create something that's very fast. So if you go back here, you have a word embedding, right? And you have a matrix multiply here. This matrix multiply can take time. But if you know that, the is a very common word and you're going to have to do this matrix multiply a whole lot, you can just calculate the value post-matrix multiply. And this will allow you to avoid doing that matrix multiply implicitly. Oh, I should mention 1,000 words per second. And I believe this was on CPU, not GPU. So that's pretty fast. This also gave strong results and beat most existing transition-based parsers at the time. So the really nice thing about this, I think, is still its speed, and you can still use this in the Stanford parser if you want to parse, like gigabytes of text or something. And we have an example of implementing this feed-forward dependency parser here, which I believe Dan wrote several years ago or something like that. So you can take a look at this if you're interested in parsing. So this is an example of like taking, kind of explicit feature design, but using neural networks to extract feature combinations and to reason over word embeddings, etc. One problem with this, can anyone think of a reason why this method might not be ideal? Like if you wanted to implement a parser, would you go with this method? Would this be a first method that you would want to try, or can you think of a reason why you might not want to do this? Yeah.
So I would probably use some sequence model, LSTM, probably, because this is like a sequence labeling problem.
Yeah, so you might use an LSTM. I agree that I also might use an LSTM. Why would an LSTM be better than this particular model? Any ideas? I'll give you a hint. What do you think about this slide? What's that? Yeah, it's a fixed orders. So that's the first thing. So like you're looking at the top 3 words in the stack in the buffer, right? Why not the 4th word? Maybe the 4th word has an influence here. You're also looking at the 2 leftmost and rightmost children and grandchildren of only 2 things on the stack, right? Why only 2? Why not 3? I think the reason why only 2, why not 3 was because, they were using a feed-forward network at the time. They had to pick a fixed dimension. And based on their experience with dependency parsing, this seemed like a reasonable dimension to use. But it is limiting the order. It also required a lot of intuition to know that these are the things that you should be looking at, for this particular task. And maybe it's different for phrase structure parsing, or maybe it's different for semantic parsing. So there's still, despite the fact that they removed the feature combination design, they still have the feature design that they used here to try to implement this. So yeah.
So what type of children and grandchildren are we talking about? Are these constituency parsing?
For constituency parsing? Oh, so for constituency parsing, you need a different feature set. This is specifically for dependency parsing.
So these are dependency parsing children.
Yes, exactly. So
how do we, during testing time, how do we know which are the children, grandchildren to make these?
Oh, so during test time, how do we know what are the children and grandchildren? That's a good question. And the answer is you can only take the ones that you have in your current configuration. So in this case, in your current configuration, stack 1 has no children. It has no grandchildren. So basically you would give null, like an embedding for null here. Stack element number 2 has 1 left child, so you would give the embedding for I for the left child. And you would give the embedding of null for the right child, and similarly for the grandchildren. So, yeah, that's a good question. Any other questions? Okay. So, given that, next I'm going to do a brief aside. This is not specifically about dependency parsing, so even if you're not interested in dependency parsing, this is a good thing to know. So when you're using trees, if you want to use tree structure in neural networks, you need a way to essentially encode tree structures and use them in your network. And why would you want to use tree structures? One obvious reason why you might want to use them is if you're doing parsing, because if you're doing parsing, you're generating trees, so you want some way to represent them. But there's lots of other reasons why you might want to use tree structure. And an example of this is, for example, for sentiment analysis. You can come up with examples where, for example, what this movie lacks in depth, it makes up for with its heart. So you see this tree-structured, essentially, representation of the sentence, where it's combining together words, and you can see this particular subsequence of the sentence is kind of positive. This particular subsequence of the sentence is kind of negative. And then what you can do is you can say, you know, I want to decide the overall score for the sentence. And given the overall score for the sentence, I can look at the left kind of syntactic constituent and see this is negative. I can look at the right one, see this is positive, and kind of reason in a very abstract way. So if I've seen X but Y, for example, X but Y is a very, very common structure in English. And normally when you see X but Y, let's say X has one sentiment and Y has another sentiment. What do you think is the sentiment of the whole sentence? A little louder. Y. It's the same sentiment as Y, exactly. Yes. So I saw you mouthing it, and it was right. So I might as well give you 3 points. So this is extremely generalizable. I didn't even need to tell you what Y, X and Y were. I just needed to tell you the sentiment of each. I needed to tell you that there was a but in between. So if you create a model based on tree structure that has a high, kind of a high connection to the syntax, then it's reasonable to say that this will generalize better than models that don't do this or need to learn syntax from scratch in order to do sentiment analysis, for example. So one example of tree structured networks are the recursive neural networks of Socher et al. There was actually somebody at CMU who did a very similar thing in 1991 or something like this, but I forgot to add the citation here. But so the idea has been around, but it was really popularized by Richard Socher and colleagues at Stanford recently. And basically the way it works is you have some predefined tree structure over the sentence. So you have a parser that already gave you a tree structure over the sentence. And based on this tree structure, you compose inputs into a vector for each node. So an example of a tree RNN, using a tree RNN could be essentially you take this movie, which is one constituent, and get a structure from it. You get hate, which is one constituent, and get a structure from it. Which is one, I hate this movie, which is one constituent, and get a structure from it. So you do this in a recursive fashion. So recurrent neural networks are also, you can also think of them as a type of recursive neural network. So you can think of a recurrent neural network essentially as a recursive neural network with a right branching tree. And what I mean by this is you have I went to the store. This is disappearing under the slides here, but here you go. So if you look at this, sorry, left branching tree. Sorry, it's a left branching tree. So you can see that essentially this is taking I and went and combining them together. Then it's combining that vector with to, combining that vector with the, combining that vector with store. So this is exactly the same thing as what a recurrent neural network does, right? So these kind of tree structured or recursive neural networks are strictly more expressive than recurrent neural networks because they can use arbitrary tree structures instead of only left branching tree structures. Is this clear or any questions? Okay. So I purposely left this tree RNN function undefined for the first part of this slide. To give a specific instantiation of it, one easy thing that you can do is just take the left vector and the right vector, run it through a weight matrix, add a bias, and take a tan h of it. So in this case, you would take these two vectors, run it through this function. In this case here, you would take these two vectors and run it through this function. Another thing you could do is, like, for example, if you had a constituency parse or a labeled a labeled dependency parse. You can also parameterize by the constituency type or the dependency type. So for example, if it's a noun phrase, you might have a different weight composition matrix here. A verb phrase, you might have a different weight composition matrix here. Or if you wanted to do something with dependencies, for example, you might have a different weight for subject, object, etc. So this was this model was quite interesting and really, I think, sparked a lot of interest in the overall area of neural networks and NLP in general. Then, like everything else, after 2014, everything turned into an LSTM. Next we have tree-structured LSTMs. There's two varieties of tree-structured LSTMs proposed in this particular paper. One is the child sum tree LSTM. And basically, the child sum tree LSTM is an LSTM that functions over arbitrary numbers of children. So, oh yeah, one other thing I should point out here is this only works over binary trees if you do it this way, because the size of W is fixed. So you concatenate two children, and you multiply it by a weight matrix to get the next input. So obviously, you need to have exactly two children here. The child sum tree LSTM actually fixes this problem. And the way it works is you have parameters shared between each child, including the input matrix, the transformation matrix, and the input matrix, the output matrix, and the update matrix. Also forget gates. And the forget gate value is different for each child, which allows the network to do things like learn to ignore children. So one example is, let's say we're doing sentiment analysis, and we have, I hate this movie. One thing the LSTM could learn to do is it could learn to just forget all of the information about I the moment it sees that this information down here is highly negative, for example. So like if this vector somehow encodes the fact that this is a highly negative constituent, it could say, look, I don't care about I don't care who's doing the hating. All I care about is hating. So it would set the forget gate to all zeros for this one, and set the forget gate to all ones for this one. So it would just pay attention to the right constituent. So this is something that the child sum tree LSTM can do. There's also something called the unary tree LSTM, which basically uses different parameters for each child up to n. So, if you have a ternary tree LSTM, it would have 3 parameters. If you have a, quaternary? What's the proper term here? Yeah. If you have a 4-ary, I'll give up on my Greek and or Latin. So if you have a 4-ary tree LSTM, you could have 4, and then any additional constituents would just be processed with the fourth one here. So these are 2 varieties. So another example of a way you can do composition is using bi-LSTMs. So what you do is you simply read in the constituents with a bi-LSTM. So this obviously allows you to take in as many constituents as you want. You can take anywhere from 1 to 50, because what you do is you just run a bi-LSTM over these vectors and take the final states as your representation here, and then you run a bi-LSTM over these vectors. You take the final states as the representation here. So this is another way that you can compose things. I forgot to add a slide. So I forgot to add a slide about this, but if you also if attention is all you need, then you can also do it with attention. So this paper also proposes a method to do attention over the constituents. So the name of the paper is this one. This is a paper that I also did with Adi, who used to be here. So basically, what I want to point out is there's lots of different ways of composing together constituents, but the basic idea of having a tree-structured RNN that composes constituents according to syntax is something that you can do. And we have an example of tree LSTMs here. I think one nice thing about this example, I can actually show the example on the website. So the wait, where is it? Is this it? So this shows how easily you can implement something like this. Basically, you just have a recursive function that goes where you call the recursive function over a tree. In this case, I think we're using the NLTK like tree reader to read in a tree. You just define a recursive function and you recurse down the tree to implement this. So this is maybe 35 lines of code, and you can see how you can do this. Okay. Are there any questions about tree-structured composition functions? I should also point out there's a really nice paper about when are tree structures necessary for deep learning of representations. This is a good empirical study where they built basically two very strong baselines, one a tree-structured one and one a non-tree structured one. And they found that for some tasks it's very useful to have these, and for other tasks it's not. It seems like you can get away with something simple like an LSTM. So I would also take the results here with a grain of salt, because these are all on English with relatively large size data sets, where both the tree structures and the data sets are, both the tree structures are good and the data sets are large. So I feel like tree structures are more useful when you don't have very much data to train your models, because they are a way to improve generalizations. So just because you see that it didn't do well in this paper doesn't mean you should give up, but it is a very thorough and good explanation, very thorough and good examination of this idea. Okay. Are there any questions about tree-structured encoders? No? Okay. So now let's go back to the main idea of actually parsing things. So I'm going to talk about stack LSTMs. And these are a method for dependency parsing with less engineering and wider context. And the idea is basically that we need to encode parsing configurations with RNNs. So as I said before, the whole idea behind shift-reduce dependency parsing is that we need to encode our configuration in our queue, our stack and our queue. So we don't want to do feature engineering. Can we encode all the information about the parse configuration appropriately? So the information that we have is the stack and the buffer and the past actions. So basically what we do is we just make 3 RNNs. So we take 3 RNNs, specifically LSTMs, and we have one to encode the buffer, which basically reads all the words from the end of the sentence to the beginning of the sentence. So these are all the things that we haven't parsed yet. We have another RNN that encodes all of the past actions that we have taken. And then we have another RNN that encodes the stack. So the interesting thing here is basically in this stack encoding RNN. And the reason why is because all the other ones encode things that we already know how to encode easily, right? It's words. We already know how to run an RNN over words. It's actions. We already know how to run an RNN over actions. But how do we run an RNN over this thing here, right? This is a subtree, so how do we do it over a subtree? And the way we do this is by embedding tree fragments using one of the syntactic composition functions that we talked about before. So the contents of the buffer are just sequences of embedded words, which we shift from. In the context of the stack is sequences of embedded trees, which we periodically pop and push from. For the sequences, we use RNNs. So for the embedded trees, basically what this does here is it runs in RNN over the head in all of the subtree embeddings to get an encoding here. And then it runs an RNN over kind of the encoded, all of the encoded subtree embeddings. So one problem with this is if you actually want to run this, if you actually want to do parsing efficiently, one way you could do this is running the RNN over your subtree embeddings every single time. So like you might run an RNN over the entire stack every time you get a new stack and then use it to make a prediction. Unfortunately, this is expensive and wastes a lot of computation. So the method that they introduce here to kind of fix this problem is something called stack RNNs. So basically you have a stack of things that you want to encode. So you augment an RNN with a stack pointer. And you have 3 constant time operations over the stack. One is push, which is read an input and you add it to the top of the stack and encode it with the RNN. One is pop to move the stack pointer back. And the other is embed, which is basically returning the RNN state at the location of the stack pointer, which summarizes the current contents. So an example of how this works is you basically start out here. You append something to the stack and encode it using an RNN. So in Dynet, you use the add input function. You then pop and move back here. You then add another input, which then uses this as your input here, and you advance. And notably, you just don't use this anymore. You can just like ignore this. You can pop it back and add another one. Or maybe you don't pop and maybe you add it to the next one here, which means that you transition here. So this is a kind of nice formalism if you want to handle things like tree structures or whatever that have to have stacks that you're encoding. I think this is also a really nice example of how you can combine together data structures with neural networks. So if you look in your C++ specification or your Python specification, you have things like linked lists, you have things like stacks, you have things like queues. And you can also think of these, like anytime you have something like this, you can also encode them by thinking, what are the operations that are defined over this data structure, and how do I need to implement them in a neural network? Of course, there are efficiency concerns with this, so you need something fast. You need something. Dynet is a good example of a network of a library that allows you to do this easily. PyTorch also is pretty good. You probably don't want to be using something like TensorFlow for something like this. So, yes. Okay. Any questions about this? Okay. So there's also alternative transition methods. All the previous methods did left to right. There was one example in the reading of arc-eager dependency parsing, which was an alternative transition system to arc standard dependency parsing. There's other ways to do this. One example is top-down dependency parsing. What top-down dependency parsing does is it basically picks the root first. then it picks the children of the root. Then it picks the children of the children. Sorry, that would be breadth first. So you pick the root first, then you pick the left child of the root, the left child of that, and you descend using a depth first fashion. One example of this is a paper called Stack Pointer Networks by Max Ma here. Another interesting thing is easy first. So this picks the easiest link to make first, so the link that we have the most confidence about, and proceeds from there. So there's an example of this in Neuroland by Kemper-Wasser and Goldberg, where they basically do this for dependency parsing. There's also some interesting papers by Andre Martins. Where they take easy first parsing, easy first tagging, and make this fully differentiable, so you can backprop through the easy first parsing process. I think this is a kind of, it's a very cool paper in that it uses lots of technical sophistication that is, it's not overly complicated. It's just complicated enough to achieve the objective here. And they introduce, for example, new operations within the neural network in order to make this possible. So if this sounds like something interesting, this is another paper that you could take a look at. Okay. Any questions about these things? Okay. So the next thing is shift-reduce parsing for phrase structure. So phrase structure was covered very briefly. So I mentioned why dependency parser before. So I think before I talk about this, it's a good idea to mention why phrase structure. One reason why you might want to use phrase structure is for highly syntactic tasks. One example of this being a task that I like a lot, which is machine translation. So machine translation, one of the important things for machine translation is to get the syntax correct in the target language and get it to match the input. This is something that you would think if you just like kind of simply look at outputs of very good neural MT systems, you would think they're very good at this, but actually they're surprisingly not good at this, at sufficiently complicated or sufficiently out of domain data. But for example, if you want to translate between Japanese and English, or Japanese or Hindi and English, or any other number of languages that have a very different syntactic structure than English, you could come up with very simple rules for things that you should be doing to transform between the two languages. So, for example, Japanese and Hindi are both SOV languages. So English is an SVO language. So you need to take the verb from the back and put it after the subject. And that's really simple to explain according to a tree structure, but it's not, especially a phrase structure. But it's not simple to explain according to just a sequence of words. So phrase structure is particularly well suited for this, and it's been quite underexplored in neural models, I feel. So anyway, how would you do phrase structure parsing? There's a lot of examples of this, both before kind of the neural boom, and also neural methods for this. One way you can do this is you have shift, and then you have reduce X, binary, unary-X, and X is the phrase label. So basically, if you have a phrase structure that looks like this, you could binarize it into a binary tree. And then you have something like the tall girl, which is your stack in your buffer. And shift would take girl, shift it off the stack. Reduce NP prime would basically take tall and girl and reduce this into NP prime. And unary might take a configuration like this and add another unary rule on top. So I won't go into a huge amount of detail, but basically if you design your transition system, it can also work for these kind of phrase structure things. It can also work for anything that you have labels on the spans. So one example of this might be semantic role labeling or something like that also, where you have a label over the semantic roles. So an interesting model for this is recurrent neural network grammars. This is interesting for two reasons. Number one, it's a good model over sentences to do constituency parsing. The other reason is that it's actually a language model also. It's a model that can calculate the probability of a sentence. It's a generative model. And when I say generative model, I think we've talked about this maybe before, but in a normal discriminative model, like all the ones that I've talked about before, if y is our tree structure and x is our sentence, we're calculating the probability of the sentence given the tree given the sentence. But in a joint model, a generative model, we can calculate the probability of both at once, which also means that if we can sum over all of the tree structures for this probability, we can also calculate the probability of the sentence. So this is interesting because this is like a language model, right? So, or it is a language model. It's a model that allows you to calculate the probability of the sentence, and you can show that in some cases this is better than LSTM models, and it's particularly better at particular types of syntactic things that allow you to generalize. So this is essentially how it works. It's a left to right model. And you have your stack. You have, which basically you build up with partially created trees. So this is the start of a sentence, the start of a noun phrase. Then you generate a few words in the noun phrase. Then you have a reduce action, where the reduce action composes all of the words in the noun phrase into a single vector. So this is very similar to the stack LSTM that we talked about before, where the stack LSTM had, subtrees, vectors representing subtrees. This reduce operation here basically does the same thing. The main difference between this and the stack LSTM that we talked about before is you also generate the words. You don't just take in the words and encode them. You generate the words jointly. This can serve as a language model as well. It also has very good parsing results. For a very long time, it was kind of the state of the art. When I say very long time, I mean like 1.5 years, which is a very long time in neural land. So it wasn't a long time before neural networks, but now we get new state of the arts all the time. So. One problem with this, though, is decoding is difficult. And the reason why is basically at the very beginning, the only information that we have, or we have no information whatsoever about the sentence. Because like language models, like any language model that generates a sentence, you need to generate it in some order, like left to right. And you're not allowed to look at the words that you haven't generated yet. Because otherwise you don't get a well-formed probability over the sentence. So at the very beginning, basically, this model is kind of working blind. And it's very hard to say, I need a noun phrase at the beginning if you don't know what words are in the sentence. So the way you can get around this is you can take a discriminative model like the stack LSTM or something, generate candidates and then re-rank them to get your final answer. Another thing that you can do is importance sampling. So importance sampling is a way to basically approximate this marginalization over all of the trees that you could possibly have. So you sample trees according to the discriminative model, and then you recalculate their probability according to the generative model. So I realize that this is a little bit complicated, but it is a very interesting model. in paper as well. There's a couple follow-ups that I just realized I forgot to add to the slides. I can go back to the I could go back to this paper, which I just talked about before. This also uses recurrent neural network grammars. In this model, basically, or this paper essentially examines, tries to interpret these models. So it looks at attention over the constituents and sees whether the attention over the, over the children. It sees if the attention over the children matches up with existing linguistic theories about, which words are the most important in the sentence. And it also sees whether you can kind of group the embeddings for each phrase according to their syntactic classes. So each phrase gets its own embedding. So the green ones, the ones in dark blue are verb phrases. The ones in red are relative clauses. The ones in PP are, S-bars. The ones in PP are prepositional phrases. The ones in light blue, the ones in yellow are prepositional phrases. The ones in light blue are noun phrases. So this particular version of the model was not given any information about what type of phrase it was, but it was still able to recover it. So I think another advantage of linguistically motivated models is, for example, if you're interested in linguistics in neural networks, linguistically motivated models and learning over them and then interpreting what they learn is a way to kind of examine linguistic theories or examine whether particular things are being learned by neural networks in a very kind of elegant way. Okay. Yes?
So how do they actually learn the TOS
the phrase embeddings. So those are just learned as part of the model to try to improve the model's parsing accuracy. So the model in the recurrent neural network grammar, I don't actually have a figure of it, but it's pretty similar to this model here. And they have a syntactic composition function using the by LSTM over the children. In that paper, it's also attention over the children. And this is just learned end-to-end to try to maximize the parsing accuracy or maximize the likelihood of the correct parse. So the interesting thing is we didn't give it any information about the phrases, but it was able to uncover that. Any other questions? Okay. So I really like this model. I think these kinds of models that use tree structures, et cetera, in the models. But I realize that a lot of people are lazy. So I'd like to give you a lazy approximation of some of these better models. And this doesn't work as well empirically, but it is very easy to implement if you want to try to incorporate tree structures in your models. And basically what you do is it's similar to the RNNG in its transition system, but instead of having like shift actions and reduce actions and syntactic composition functions, basically what you do is you turn this tree into a sequence of symbols, and then you run a sequence model over it. And the sequence model predicts the sequence of symbols, and then you turn this back into a tree and you evaluate it for its accuracy. So yeah, the advantage is this can be done with simple sequence models. The problem is that it doesn't have any explicit composition functions. So really, this will only be as good as the amount of data you can provide it. And in order to get this model to really work well, they did things like use an existing parser to parse a huge amount of data, and then kind of use that to bootstrap this model. So like this model, it's fine to use this if it's a shortcut to get you where you want to go, but it won't work as well as the more sophisticated methods. Another problem is it's not guaranteed to output well-formed trees, and if it doesn't, they have a simple heuristic to add parentheses until it becomes a well-formed tree, which is a kind of hacky heuristic that you might not necessarily want to be using. So to go back a little bit, why would you want to insert linguistic structure? There's a really interesting study by Kunkoro et al. 2018 where they compare a sequence-based LSTM. So this has no syntax whatsoever, with a sequential syntactic LSTM, so essentially where we linearize the trees, with the full recurrent neural network grammar that includes the syntactic composition function. And they compared the perplexities, and the perplexities of the two models were pretty similar. They weren't hugely different between the two, which might make you think that, you know, hey, we don't need to worry about modeling syntax because, you know, they look very similar with respect to overall perplexity. However, they did a very interesting thing here, which was they evaluated it on noun-verb agreement, where noun-verb agreement is, you know, it's a thing in English that we know happens. Humans are very, very good at doing this if you're a native English speaker. Basically, okay, I won't say very, very good, but pretty good at doing this if you're a native English speaker. And what they did was they created sentences where there were distractors in between the actual syntactically related words. So in this case, you have parts of the river valley have or has. And the answer here is parts have, but if you just take the valley, it's the valley has. So what this graph is here is basically they calculate the probability of this and the probability of this, and they see whether the model gave the correct one a higher probability than the incorrect one. And when there are no distractors in between, when there's no intervening words to kind of throw off the model, actually the regular LSTMs do a slight bit better. But the moment you start adding distractors, if you have one, they're about the same. If you have two, the syntactic RNNG starts getting better, and then if you get 3, 4, 5, you start to see a huge difference in the ability of the model to, you know, judge whether this is correct or not. So I think the reason why this is interesting is this points out that the model that incorporates linguistic structure is generalizing much better at these really difficult cases. And so if you're interested in robustness in models of NLP, and you're tired of your neural MT system working really well until you put it into a new domain that has different words than your training data or something like this, this is one way you could do this, because this will allow you to generalize over syntactic structures which are invariant across domains. Whereas, you know, a regular LSTM-based model or whatever might be thrown off by this. Okay, so that is all I have for today. Are there any final questions? Okay, if not, I will finish up. Thanks a lot.